it rings. Okay, I'm going to do that. Is that okay? Is that okay? Sorry, I just don't like ringing. Okay, so anyway, so the problem with this is, so you're a varied bunch. So many of you know a lot about fluid mechanics. Some of you know more about it than I do, and well, most of you know more about it than this guy. But some of you know more about it than I do, and whereas some of you haven't really been exposed to it that much and are just here to learn. And so we felt that at the beginning of the school, because this is a school, it was necessary for somebody to get up and give an introduction to the subject. That is, to start with the Navier-Stokes equations and go from there. Now, the problem with giving such an introduction, as I learned last night or yesterday when I was writing it, and by the way, there are these notes, and you will get these notes. I'm not sure that you're going to want them, because I'm not sure they're very good, but I do have notes. I didn't, so you'll get them. There's, but so the problem with such a subject is that I'm trying to figure out how I can not fail, and here's my concern. That is, if you know the subject, I'm about to spend the next hour and a half boring you. If you don't know the subject, you're not going to understand a word, because I'm going to go much too fast. So because I have to, my job is, I think I have 3 hours, and I have to cover the whole subject. That's what I have to do. And of course, I'm not going to do that. And at some point, I might get bored and do something else. But anyway, so that's what I'm supposed to do. So okay, so that's the goal for today. And so what I would encourage you to all do is remember, this is also the other goal. Remember, I already told you, is for you guys to get used to yelling at people. Maybe I'll write down some equations that are wrong. But what I'm going to do is give you at least a view of the subject of hydrodynamics or fluid mechanics and what the main ideas are. And if you disagree, then you should argue, because that's fine. It'll make it more fun. Okay? So let's get started. So the first thing that one has to do in a lecture on Introduction to Hydrodynamics is write down the Navier-Stokes equations. So I'm not going to derive them, but I'm just going to write them down. So if anyone would like a derivation, we can do that next time. But I propose to ignore that. Okay, so I'm going to just write them down. So rho plus. So I'm also setting notation plus gradient plus F. So this is the equation of momentum balance. Actually, let me write down the equation of mass conservation, and then let's talk about them. So there's an equation of mass conservation. So dt rho plus the divergence of rho u is equal to 0. So these are almost the entire equation of motion. They're not actually complete, as some of you know, as I will tell you in a moment. But these are the equations of motion. So, okay, so what do these symbols mean? So we're imagining a fluid, like the gas that's in this room. The fluid has a density rho. So rho is a density, which is in general a function of x, y, z, and t. There's a velocity field, u, which is a function of x, y, z, and t. There is a pressure, P. So P is a pressure, which is also a function of x, y, z, and t. And then we have an F. So this represents a force. So this is a force. Of course, there are lots of types of forces that could be acting on our fluid, and throughout the school you will see many different ones, and so for the moment let's just leave it as F, and we'll talk about it later. So let's see, what else do I have to say? So these two, so eta and zeta. So eta is what people call the dynamic viscosity. Does anybody know what zeta is called?
So it's zeta, it's not rho, right?
That's zeta, sorry. Oh yeah, that's zeta. Does anybody know what zeta is called?
Both.
So it's called the bulk viscosity. Just going to call it the second viscosity. The bulk is just as good. Viscosity. I always actually forget what these words mean. So these two terms represent dissipation mechanisms in flow. So this is force. This is dissipation. Okay, so this is inertia. So this is basically, this is Newton's laws, this is ma, so rho is the density of a particle of fluid, so this is the mass of a particle of fluid. So the acceleration, and this is one of the critical parts of the subject, has two parts. The two parts basically come from the fact that we are writing the equations in what people call the Eulerian frame. That means we're writing the equations in the lab frame. And the point is that if I study the velocity of a molecule or of a set of molecules that are localized right here, that velocity can change for two reasons. Either it can actually accelerate, there can be explicit time dependence that causes it to actually accelerate, or the molecules over there, which are actually moving, they could advance into my frame and cause the velocity to change. And so the acceleration has two components which represent those two physical effects. There's then an equation for mass conservation. So rho is the density and u is the velocity. This is conservation of mass. Within this formulation of the equations, the pressure is actually given by an equation of state. So, sorry, this is bad blackboard skills. Let me show you bad blackboard skills. But look at the bright side. Most of the people probably are going to show, are going to give PowerPoint. So at least you don't need to use PowerPoint. So, okay, the pressure is given by an equation of state. P is a function of rho, and of course it could also be a function of the temperature, which brings up the equation that there should also really be an equation for the temperature, which I'm not going to write down. The temperature, of course, can also advect and diffuse, and can change the local equation of state, which can then couple back the momentum equation, which couples to this. And these equations are basically, the full, they're more or less the full Navier-Stokes equations. And so the beauty of this subject, in a very real sense, is that every phenomenon that exists in simple fluids exists as solutions to these nonlinear partial differential equations. And the question is to really understand how the different phenomena can be understood as solutions to these equations. Let's see. Do I have anything else to say? Does anybody have any questions, comments about this? Have I said anything wrong here? No. Yeah, well, okay.
So Michael, so you mentioned temperature, so is this assuming that there's some near equilibrium situation? Or?
Right, so we're assuming that there's local thermal equilibrium. So we're assuming that there is a temperature. Of course, if one wants to push beyond that and move into a regime where there isn't a local temperature, or that the fluid is not in local equilibrium, namely it's not described by a local Boltzmann distribution or whatever, then the equations become more complicated. And that can occur in the dynamics of fluids, but it tends to occur in gas flows that are, and that's, I'm going to just rule out of bounds from the point of view of this lecture. Although on the other hand, if anyone leaves here today saying, gee, I wish you would talk more about gas flows, guess what? There's another lecture tomorrow, so we can do that tomorrow if you want. But so I'm ruling that out of bounds. So, okay, instead, what I want to talk about today is, and this is going to be, at least in a certain sense, very elementary, and I hope that, you're either going to understand or be bored by this, but what I want to do is I want to talk about how it is that one can understand solutions to equations like this. This is an unholy mess, right? If you just look at it, it's an unholy mess. And basically, at least my characterization would be that over the past, it's 2011, over the past 150 years or so, people have figured out ways of thinking that basically allow one to take this big mess of equations and at least really understand the essence of why the solutions are what they are. And what I want to do is tell you what I think at least the most important ideas are in organizing and unraveling this. And okay, so the most important idea. Most important. So actually, I should write it. So what are we supposed to do? What to do? This is the next. And of course, at the beginning, like in the 19th century, what people did, we'll talk about what people did in the 19th century. We'll talk about that. I'm not going to tell you what they did. Because if you read the books and you ask, what was it like then? People didn't really, I think it was not understood what I'm about to say. It was sort of understood, but it wasn't understood in all of its glory. So to me, the most important idea in this subject, and this is, I may say something provocative for everyone to yell at me, was invented by Prandtl. Who knows who Prandtl is? Who's ever heard the word Prandtl? P-R-A-N-T-T. Seriously, who's heard of Prandtl? No, you don't have to. If you haven't heard of him, it's fine. You haven't heard of him? Good.
It's pronounced differently in every country. I think.
Oh, really?
Yeah. That's why.
How do you pronounce it?
Oh no, I knew who you meant, but I think
Well,
people were.
how do you pronounce it? Who pronounces them differently?
Pronto.
How do you say it?
Pronto.
Anyway, he invented what I think is the most important idea as a subject. And I'm going to give it a name which is a little different than the name that he gave it. And indeed, his version of it is much more subtle than the way we're going to start out. This lecture is essentially going to start out with the crudest possible version of this idea, and it's going to become increasingly more subtle. But the most important idea is what one might call the idea of dominant balance. Okay, so let me explain to you what I mean by this. So the idea of dominant balance is the following idea. So we have this equation. It's a nightmare. There are all of these terms. It's terrible. And there's no way that you're ever going to understand something in which there are all these different terms or all of these different effects that are basically going on at the same time. It's just not possible. In fact, so what are you supposed to do? So what you're supposed to do is you're supposed to look at the equation and you're supposed to hope that in the particular situation that you're interested in, that many of the terms don't matter. And so you delete them. That's what you do. And basically the game is you keep deleting things until finally you have something you can understand. Then you understand that, and then you have to decide if it's correct. That's the idea of dominant balance. Okay, and it turns out, and so there's the crudest version of dominant balance, which probably those of you who have taken fluid mechanics are subject to. And I must say that the first time that, actually I never, this is perhaps an admission, I'm on tape actually, so that's actually good. I've never taken a course in fluid mechanics. For whatever it's worth. So I never took a course, but I did read the book. I have taught the subject before, and I have read these books. And I must say that when I started reading these books and it did what I'm about to do, it just seems so boring to me. But okay, and so but I'm going to try to convince you it's not so boring. So okay, so this is what you're supposed to do. So you're supposed to figure out what to neglect. Okay, so if you want to figure out what to neglect, then you need to basically be able to estimate the sizes of the different terms in the equation, right? Because you don't know, I mean, in a particular situation, what's going on, so you have to be able to estimate the sizes of the terms. So let's estimate the sizes of the various terms. So let's estimate sizes.
But Michael, when you say that this is what we call duty physics, I mean, everywhere in physics we do that.
Sure.
Dominant balance.
I completely agree. This is everywhere in physics. No, I completely, this is a good comment. So dominant balance, this is not unique to fluid mechanics. This is the way that all of physics works. I mean, if you want to study an atom, then you're allowed to neglect the effects of quantum chromodynamics. Whatever. That is, you're allowed, that this is how everything, this is how science works. If you study biology, right, then you're allowed, if you're interested in microtubules, you might consider yourself allowed to neglect the variations in the concentration of some chemical. This is how science works. This is not unique, and I think this is very good. This idea is not unique to fluid mechanics. To me, this is the most important idea in theoretical science, period. What is unusual, I think, about fluid mechanics in this regard, and Leo, you can argue, or anyone can argue with me about this, is that I think that this is a subject where the subtleties that can come when you delete things and the issues that come up really first became apparent in all of its glory. And in particular, Prandtl's example, which we will discuss. That is, I think this is a much more subtle game than you think. Part of the reason that I think this happened first in fluid mechanics is that, as I said, it is a very old subject. So it's been around for a long time, number one. And number two, I mean, even the physicists don't like studying nonlinear partial differential equations. So, but we have no choice. Okay, so let's estimate sizes. So let's imagine, so you have to estimate from something. So let's just imagine that our flow, so imagine that the flow that we have has some velocity scale, U naught as the velocity scale. It has some length scale, L, that's the length scale. And I don't know, so like for example, at some point today, if we get to, and I'm going to tell you my theory of fireworks, which is, I think, wrong. But anyway, so just to give you an idea of a velocity scale in Einstein, so those explosion thingies that you saw last night, they were going outwards at some speed and there was some length. So that's velocity scale and length scale. Okay, and then what you're supposed to do is estimate the sizes of the different terms. So let's just do this. So let's see. So let's estimate the size of du dt using these numbers. Well, if I want to create a time scale using a velocity scale and a length scale, then the way to create a time scale that is something that has the dimensions of 1 over time is to consider U naught over L. So U naught over L has the same dimensions as d by dt, and U, of course, has the dimensions of U naught. So what I might say is that the size of du dt is U naught squared over L. Now similarly, the size of U dot grad U, well, let's see. So U has a size U naught. When I take a gradient, I'm dividing by L, and then I'm multiplying by U naught. And so that also has a size U naught squared over L. So that's convenient. According to this estimate, both of these terms have the same size, namely U naught squared over L. So then what we want to do is compare that, and this is the game, because we want to delete things. So one of the principles of life of deleting things, if you're ever interested, is whenever you delete things, you always delete something relative to something else. You're not allowed to just say, quantum chromodynamics is small, and I don't care, so I'm going to delete it. You have to compare it to something else, right? So therefore, we have to actually take another term in the equation and estimate its size and compare the two. And the sort of what I'm going to do right now is viscosity. I'm going to eventually, actually, these flows are going to become incompressible. The bulk viscosity is going to go away. But so for now, I'm going to just do this one, although you can obviously do this with more terms. I'm running out of blackboard. I'm not doing a very good job using blackboard. I apologize. But the viscous term, basically, eta Laplacian of U, well, that has the size eta U naught over L squared. So that's the size of that. And now the game is that what we need to do is compare the sizes of these terms to each other. So if I want to consider the ratio of the inertial terms to the viscous terms, well, that's, what is that? So that's, oh, and I forgot the rho, remember, there's a rho here. So I have to multiply by rho. There has to be some density still. Rho. So the inertial terms have the size rho U naught squared over L. The viscous terms have the size eta, what is this, U naught over L squared. And this ratio, when you work it out, is U naught L over eta over rho. And this is a famous number, which is called the Reynolds number, thank you. So this is called the Reynolds number. And people, it's so important that people actually there are other reasons for this too, but this quantity, eta over rho, is called nu. It's what people call the kinematic viscosity. It has the dimensions of a diffusion constant. And the Reynolds number is the number that differentiates between the sizes of inertial terms and viscous terms. And so the thing about fluid mechanics as a subject, and this is the part that I guess I found when I started reading these books, and I still find it actually, I found to be rather prosaic, is that there are all of these dimensionless numbers. Because so that's it, Reynolds number, that's one dimensionless number. So I could now spend, and if this were an actual semester course in fluid mechanics, and I were teaching it, I would have to spend like a week going through every dimensionless number that you can imagine. So I'd have to like compare this to that and that to that, and you would all fall asleep. You see? But the point is that that's important because you have to figure out what to delete. And it's actually so important in the subject that the whole subject is organized around this. If you go, has anyone ever gone to this, what do they call it, this APS fluid mechanics meeting? Has anyone ever gone to the APS fluid mechanics meeting? Has anyone ever looked at the list of sessions? Do you realize those sessions are organized around these dimensionless numbers? Are you a high Reynolds number person or a low Reynolds number person? Are you interested in capillary interactions? What is your fruit number? This is how the whole subject. It's amazing. It's like the whole subject is organized around these damn dimensionless numbers. And that's basically the thing about what terms the people who are working on them want to delete. And we all have our thing. And you'll see the lectures all have their thing. Some of them are high Reynolds. Maybe you guys have your thing. High Mach number, low Mach number. But okay, but the point is that if the Reynolds number, let's just focus on that for a moment, if the Reynolds number is high, then what that means is that the inertial terms are very large. And the viscous terms, and in particular, the inertial terms are much smaller, are much bigger than the viscous terms. And I thus, at least within the spirit of the philosophy, I thus should be able to just delete the viscous terms entirely and see what happens. So, here, let's see. Let me just want to... Right, okay. So later in this talk, as we get to it, which hopefully I'll start accelerating these well. So I wrote much of this when I was on the airplane. So I decided when I was on the airplane to calculate the Reynolds number of the airplane. So I'm not going to do that for you because you're going to be bored. It's in these notes that you're going to get. So I calculated the Reynolds number of the airplane to be 10 to the 7th. I don't know if that's right. That's right. God, I basically said that the speed was, I don't know, it was 200 miles an hour. I don't actually know what it was. So that's like 10 meters a second. That was what I got in the airplane. And the airplane, I figured had a size of about 50 meters. And then I turned out, I know the kinematic viscosity there. That's 0.1 centimeter squared per second. I have some of these numbers in my head. We're actually going to calculate that in a little while. Actually, we're going to calculate the kinematic viscosity. Because you know what the hell? I mean, these are numbers you know a couple bucks. We should be able to calculate them. But for now, let's leave that. Anyway, so I got, and it's in these notes that you'll all get. And if it's wrong, you'll tell me, I got 10 to the 7th. So what that means is that in my airplane, this is amazing, the inertial terms are 7 orders of magnitude bigger than the viscous terms. So therefore, if you're like interested in airplanes, you're totally good at deleting this. And actually, you might as well delete that too. So you're totally good. That's just an amazing thing. So we've just gotten rid of it. So now isn't that great? Now our equations are simpler. So, and that's the thing. So now if on the other hand you were a small Reynolds number person, so small Reynolds number people are people who study things. Is anyone here a small Reynolds number person? Actually, most of you are small Reynolds number people. So I'm sorry. Okay, so you guys, that is you small Reynolds number people out there, you study things which are very slow. They're very, very slow. And so for you, and you don't like inertia, so what you do is you delete those terms. You often, actually, most of you probably, I don't know of any small Reynolds number people who keep this term. Although that would be an interesting thing to consider. In fact, if anyone's bored, why don't you try to figure out if there's a small Reynolds number problem and keep that term too. Everyone delete that. Then you get to delete this. And now your equations are linear. The small Reynolds number people are all very proud of themselves. When they give talks, they stand up and they say, my equations are linear. Have any of you ever said that? Probably. It's at the beginning of talks, because we all put the equations are linear, reversible, blah, blah, blah. So, okay. And there's all this stuff about that, but that's just deleting these terms. So, okay, and then there are lots of dimensionless numbers. And I don't know, in these notes, I like, you know, I felt like I needed to put more in. I'm not going to go through this. That's the good thing about printing this out. It might be wrong, but at least it's not. So I like put in other dimensionless numbers. So I'm just going to tell you what I put in. Oh, the next one I put in was Mach number. So the Mach number is an interesting one. And actually, let me just make a remark, and this is something you can think about. The Mach number basically comes from the following consideration. So you might want to consider a situation in which the density of the fluid that you're studying is essentially constant. So if the density is essentially constant, so let's see, let me erase. So if I make rho essentially constant, then if I look at, so suppose I say that rho is essentially constant. So I'm allowed to do that. So if I do that, then if you look at this equation, you say, well, if rho is essentially constant, then the time derivative of rho shouldn't matter because it's constant. And it's constant, so I should be able to pull it out here. So now that's gone. That's gone. So there. And now rho is constant. But now what's happened is something magical. So now the pressure, which used to be determined by the equation of state, it can no longer be determined by the equation of state because rho is constant. Let's just assume the temperature is constant too. We're ignoring temperature. And so now actually the pressure becomes what is essentially a Lagrange multiplier in these equations whose job is to project out and make sure that the velocity field that it's solving for is always incompressible. So P is a Lagrange multiplier for incompressibility, namely for the divergence of U being 0. Now if the divergence of U is 0, then you get to delete this bulk viscosity thing. So let's delete that. And that's the approximation that happens when you assume that rho is essentially constant. Now, so the question is, and this is actually the thing I want to ask you, so if you make rho, so the question is, so I just made rho constant and all of that fell out. So the question is, under what conditions is rho essentially constant?
But then where does the spatial dependence of P come from?
So the spatial dependence of P comes from the fact that, that P has to be spatially dependent in order to, point-wise in space, ensure that the divergence of U is 0. So you have to, so said differently, one way to do this is if you simply take the top equation and you take its divergence, then basically what you discover is that this term goes away because this is the time derivative of the divergence of U. The viscosity term goes away, so it's now the Laplacian of the divergence of U. So you now have Laplace's equation for the pressure, and with a source, which is the divergence of U dot grad U, and since U dot grad U, since that's heterogeneous, the pressure is going to be heterogeneous. So the spatial dependence is required in order to basically enforce incompressibility. So okay, back to where I was. So I said rho is essentially constant. So the question is, under what conditions is rho constant? Mach number is small. Okay, so Mach number is, so the Mach number is small. So Mach number is, Mach number, so I'm not going to, is the speed, basically, what would I call U naught before, over the speed of sound of the gas. The speed of sound of the gas is given by, so the diffusion rho, this is classical thermodynamics, blah, 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 is the square of the sound velocity of the gas. So, okay, is this the only situation? So this is my question. And I got, so is that it? So that, I mean, that was a hypothesis. So certainly if the Mach number is small, then sound is not important in the flow that you're considering. And one of the ways in which the density of a fluid varies is through sound. That's how the reason that we're having this conversation at the moment is sound. If I break this, then you'll have to stop recording. And I'll relieve all of the other lecturers in the whole school of the pressure. Anyway, but so the question is, and I'm not going to answer this at the moment, I'm just going to ask you to think about it. So the question is are there other conditions? That is, when the Mach number is small, is it possible for the density to not be constant? That's just something for you to think about. Okay, so but anyway, now, so this is all boring, right? I mean, it's boring. I mean, basically, we started with this equation. We started estimating sizes of terms. You know, this is sort of elementary. This is what should be taught in first-year calculus, but isn't. It takes people much longer to learn it. You know, that basically you just estimate sizes of derivatives of things, and it's totally boring, and it seems completely boring. Okay, but now let me explain to you why it's not boring. Okay, so this is why what I just said is not boring. So the reason that it's not boring is because it can be wrong, and when it's wrong, you've always learned something fundamental. Seriously. So I would like to give you right now one example of a case where, you know, this type of reasoning can be wrong. And I'm going to consider a problem which, I don't know why I put this problem in there. I just felt like I should calculate something because it's getting to few words. So I'm just going to show you an example, and this is sort of an advanced example. I don't know how advanced this is. So this is an example of what can go wrong in a very, very simple problem. So I want to consider the following very simple problem. So okay, so this is titled not foolproof. So what I mean by not foolproof is I'm going to show you an example where the Reynolds number is small. This is my goal. I want to show you an example where the Reynolds number is small. But on the basis of estimates that you would make, it's much smaller than the other terms, than the viscous terms in the equation. But yet, if you neglect the nonlinear inertial term, you have a fundamental misunderstanding of the flow. So I'm just going to show you a simple example of that. And this what I'm about to show you was discovered by Lord Rayleigh, and it was sort of an interesting discovery. Okay, so here's the example. So I want you to consider a plate. So this is an infinite plate. Infinite plate. Infinite. Okay, and I'm going to imagine that this plate is oscillating back and forth according to a law. It's oscillating sinusoidally back and forth. So I'm just going to say U plate has some magnitude U plate, and then it's times. Actually, I don't think this is I'm going to just write E through T. So just take the real part. So that's the velocity of the plate. And what I want to do is figure out what's happening to the flow, and let's just focus on the flow in the upper half. You can do the lower half if you want. So let's just go, and now we're going to use these equations, and we're going to try to figure out what's happening. So okay, so let's first look. So now it's infinite in this direction. So I'm going to call this direction x, and I'm going to call this direction y. So the system is infinite in this direction, so there is no spatial dependence in the x direction, because it's infinite in that direction. So if I were going to write down the velocity field that occurred in the fluid, u, then the point is that velocity field can only depend on y, because there's no spatial dependence in the x direction. I mean, we do expect, right, if it's oscillating back and forth here, that if you go far away in the y direction, eventually the flow is going to go away. So we expect it to go zero far away, so there will be y dependence, but it can only depend on y. So now, so let's see. So let's write down the divergence of U condition, and what I'm going to do is write that U, the velocity field, I'm going to say that it has two components, which I'm going to call the x and the y components, which I'm going to call little u and little v. And then the divergence of U is given by the partial derivative of U with respect to x plus the partial derivative of v with respect to y, and we're setting that equal to 0. And now the game is that since the flow only depends on y, that means that, of course, this term vanishes. And so now what we learned is that the partial derivative of v with respect to y vanishes, and that means that v so that means that V is a constant. But since at the surface of the plate, V is 0, because the plate is only going back and forth. I didn't tell you that the plate was moving up and down. That means that V is equal to 0. So that means that the velocity field is actually U is U of y, so it's actually just U of y pointed only in the x direction. So that's the velocity. This is the simplest thing you can possibly do. So okay, so now what I'm going to do is take this, which we've now discovered, and I'm going to put it into the flow equations and see what we get. So this is just a simple little exercise. This isn't very exciting, I apologize, but there is a point. I have a point I'm going to make, because I just want to show you that things can be more subtle than you think they are.
Michael, are you assuming like you can't have symmetry breaking in the x direction, so the velocity becomes, even though it's, the boundary condition is homogeneous in the x direction, you break translational symmetry?
So I'm assuming at the moment that the velocity field has no dependence on x. I will break that, because that's when it becomes interesting.
Say again?
It becomes more interesting when you break that. I mean, you're pointing out quite correctly that, what the hell is this, an infinite plate? There's no infinite plate. Even if, right? So that means there has to be some x dependence, and so it's going to become, anyway, we'll get there. Give me a minute. So okay, so now I'm going to take that velocity field and plug it into the equation of motion. So let's see, so what do we have? We have rho, if I consider the x component as du dt plus u d by dx of u plus v d by dy of u minus dxt plus eta times dxx plus dy of u. Now, of course, since u only depends on y, and since v is 0, we don't have this term. So the nonlinear term actually vanishes identically. It's not even this small. It vanishes identically because of the assumption about the nature of the flow. The pressure gradient, there is no pressure gradient because there's no flow. That is, actually, let me do this. So the d by dx vanishes, and so now basically what I have is that rho dt of u is equal to eta dy of u minus dxt, and I would like to argue that the pressure gradient has to be 0, and I think what I'm going to do is I'm going to say, well, the flow only depends on, pressure gradient has to be 0. I think I'm going to appeal to boundary conditions far away. I'm going to appeal to boundary conditions as we get very, very far off the plate. Since the pressure gradient, that is when I go far up in the y goes to infinity direction, then there is no pressure gradient. I'm allowed to specify that, and so therefore it has to be, and it's 0 there, so therefore it has to be 0 everywhere. So that's now also gone, and now I'm left with this really simple, trivial little equation for the velocity. Now, this equation is called, his name. No, sorry, it's the diffusion equation. I'm just trying to make this interactive. I remember, I told you this was going to be, this lecture was going to be a failure. At least I admitted it. But you're either going to be bored or it was going to make no sense. So hopefully I'm at least in half. So so this actually, if I divide by rho, then if I divide by rho, which I can go to blackboard, this is new. So this is the diffusion equation, and what I would like to do is find the spatial dependence of the velocity field. So the way that you do that, and this is really very simple, is I just say that u, which is a function of y and t, is equal to e to the I omega t times some function, let's call it f of y. And if I then plug into this equation, then the d by dt brings down an I omega. So I have an I omega f is equal to nu f prime prime, where prime now means derivatives with respect to y. And this is now a second order differential equation that has two solutions. The solutions to this are basically a linear combination of, so let's see, so if I, so the solutions to this are basically e to the, let's see, e to the y, let me say, e to the y over delta times, I have to take the square root of I. So the square root of I is e to the I pi. Sorry. So this is either, this is 1 plus or minus I. No, minus, this is important, I have to get the signs right. So no, it's minus, okay, I'm going to do this more carefully, so this is the danger. Now I'm not doing it carefully. So okay, so I have to take the square root of I. So what is the square root of I? So I knew I was going to embarrass myself. soon enough. So here we go. So I is e to the I pi. So this is either e to the I pi over 2.
Oh,
E to the
pi over 4.
2, e to the I pi over 2. So this is e to the I pi over 4, right? And then I'm supposed to add e to the 3. Am I getting this right? 3 over 4. I told you I was going to embarrass myself. Just because I'm embarrassing myself. So I don't want to, I'm just showing that I can't even take the square root of I. 2.
Actually, we cannot see it there.
Oh, good. That's perfect. I'm just trying to figure it out for myself over here. If anyone else wants to figure it out, you're welcome to do that. That's so this is, oh yeah. So okay, I got it now. So there are 2 solutions. This is also an exercise in how you teach when you don't know what you're talking about. So I got it. So the general solution is f is equal to a constant times e to the minus 1 plus I over delta times y plus b to the e to the plus 1 plus I over delta times y. So, and the point is that, so there are 2 solutions, and the point is that one of these solutions grows exponentially as y gets big, the other shrinks exponentially, and since we're interested in a solution where the solution goes to 0 as y goes to infinity, the growing one dies, and we then have, and I have to tell you what delta is, I owe you the formula for delta, and then if you sort of go back, you have that u of y, I'm sorry, I know this isn't very exciting, but hopefully it will become more interesting in a minute, is e to the I omega t times u plate times e to the minus 1 plus I over delta times y. And delta is given by the following formula. It's given by the square root of 2 nu over omega. And this is the length scale. This is the typical length scale over which the velocity of this oscillating plate starts out from one value and goes to 0. So that's the solution. It's not very exciting. This is called, it's given a name. Everything in fluid mechanics has a name. And this is giving a name. This is called the Stokes layer. And it's sort of boring. Okay, so now let's think about this for a minute. So let's see. So u dot grad u was 0, exactly. So the size of du dt is, of course, of order omega times u plate. And I'm allowed to make omega as little as I want. I can do whatever I want. I'm going to make omega, my plate's going to only oscillate once a year. But what this says is that even if I do that, at least, actually, this is a question as much as a statement. I really can't neglect the d omega dt, the du dt, relative to the viscous terms. I mean, at least if I do that, then I miss this behavior that we're seeing, which is that the velocity field decays from one value to 0 as it goes to infinity. So if I don't, I mean, that is, if I don't keep it, even though it sort of seems small, I mean, omega times u, right? That seems then I'm making a fundamental error, and the reason for the fundamental error, and this is sort of one of the things that happens in fluid mechanics frequently. This is a simple example. Is that when if I look at this thing, if I want to compare the du dt to this term, I have to take y derivatives. And the problem that I have is that unless I actually solve the problem, I don't know what sets the scale of the y derivatives. I mean, you could say it's the length of the plate, but that was infinite, so you can't use that scale. And there is no other scale, so now you're in trouble. So you can guess. So you see, this is a case where the canonical wisdom, this is very simple, I'm sorry, it's embarrassingly simple. The canonical wisdom sort of fails because you can't, I mean, what length are you going to use? And what happens actually is that the length turns out to be delta, which actually depends on omega. So actually what happens is, in this solution, right, is that even if omega is small, so it looks like the u dt is small, delta actually is becoming enormous. So that 1 over delta squared, which is the second derivative of y, basically keeps pace with the omega. And that's basically how this works. So deleting things can be tricky. But this isn't the most subtle part of this problem. So now I'm going to show you the more subtle part. And this sort of relates to what Leo said. So I mean, look, so there are no infinite plates. Yes.
Can't you generate the time, the length scale with U and omega? I mean, the way you did it with the other problem that you initially mentioned, you did U naught over L is the time scale. So what if you actually made the length scale with omega? Because omega.
Oh, no, to be sure, no, exactly. So, okay, so the right way to talk about this is to make a length scale using omega and say, well, look, there's a length scale. So look, I'll give you advice. If you ever see something oscillating, there's always a length scale, the square root of nu over omega. Your first reaction when you see something oscillating, you always should compute the square root of nu over omega and see how big it is. Very important. But that's a different idea, right? There's not an L. Like, we started out with this philosophy that there's an L. This was a generated L. And this is a very simple example of a generated L. I mean, it's so simple that it's almost embarrassing. Like, why is he wasting my time telling us this? But the point is that again and again and again, there are generated scales and generated time scales and length scales and things like this. And the estimates that one thinks one's making when one goes through and does this dominant balance thing, I'm convinced that the time scale of the flow is a second. Well, what if you're wrong? So, when I say the time scale is a second, because, the length scale is the size of this eraser. Right? So, and that's it. That's the time scale. And you say, oh, okay, good. So that means you can delete it. But the question is was I right in generating that scale? And this is why the subject, I think, is actually so interesting, is that what often happens, and this is not rare, it's almost, anytime anyone does, that is the system generates, it actually generates scales. It generates length scales and time scales that you have to solve as part, and understand as part of solving the problem. And indeed, that's the question, right? That's often the question is, what are those length and time scales? So, and this is just a very, very simple example. So let me show you something else that can go wrong, because I actually think this is sort of confusing. So let me show you that if you do what Leo suggested and break towards spatial invariance in the x direction, that actually the nonlinear term becomes critically important, even if the flow velocity u, plate, and omega are extremely small. Well, let me just show you that it's so important that if you missed what I'm about to tell you, you will miss the whole point of the flow. So, okay, so now why is this? So, look, there are no infinite plates. This is the other thing about this subject. And of course, as Leo alluded to at the beginning, this is true of all subjects in science, but it's just put on such a clear platter of fluid mechanics that it makes it interesting. Is that we start with idealizations. Consider an infinite plate. Well, there are no infinite plates. You say, well, if I'm a little, micron-sized bacteria and I live on this eraser, then it's infinite. Well, no, actually, it's about, what is it, micron? It's about there are about 1 billion body lengths. It's not infinite. So that means there is going to be some spatial dependence. Even if you live in the middle, there's going to be some. It's going to be weak. It might be small, but there's going to be some. And that's not what I want to talk about. So let's suppose that we go through and we re-examine this problem, but that we imagine that there is weak spatial dependence. And I'm going to do this very sloppily because we're doing it very quickly. It could be done much less sloppily, but hopefully this is okay. If anyone wants me to do things less sloppily, we can spend the whole day tomorrow doing this unsloppily. But anyway, so what I'm going to do is I'm going to say that now that the velocity of the plate, so I wrote u plate e to the I omega t. That's what I wrote. But now what I want to do is I want to imagine that u plate, the velocity of the plate depends on x. And I want to imagine that it does so in a very weak way. That there's a very weak dependence on x. So imagine that the dependence is weak. So what do I mean by weak? Well, now I can actually define weak for you very, very precisely. So we have discovered by solving just the infinite plate problem that there is a length scale, namely the square root of nu over omega, which is the characteristic scale over which the velocity of the plate decays as you go away. So there's some scale delta. So what I want to do is I want to say that what weak means is that the characteristic scale over which the velocity of the plate varies is much longer than this boundary layer thickness, this square root of nu over omega thickness in the y direction. So namely, so what I want to say is that, so I don't know, so let's say, so u plate over u prime of plate. So this is sort of like the length scale of variation. I want to say that this is much, much larger than delta. Which means that the essential feature of the calculation that I just described is going to remain the same, because the only thing I've done is I've added a weak horizontal dependence. So now, So the question is what happens? And what happens is apparent. So I mean, I'm going to do this quickly because I don't want to spend a lot of time on it. So the first thing that goes wrong is that, remember, we decided before that the vertical velocity was non-zero. And the reason that the vertical velocity was non-zero, we decided, was because of the divergence-free condition, namely that dxu plus dyv is equal to 0. So, and because of that, we decided that, well, you know, dxu is 0, and therefore dyu is 0, and therefore, no, so dxu is 0, and therefore dyv was 0, and therefore v was 0. That was our argument. But now you see all of a sudden dxu is non-zero. So now since dxu is non-zero, then dyv is non-zero. And in fact, we can just evaluate what v is. So dyv. So first I'm going to assert this solution that I wrote down before, this still holds. The only thing I have to do is put an x there. It still holds. So why does it still hold? I mean, approximately. We're not doing a very good job of numeric. Well, the reason it holds is because the velocity of the plate is varying on a scale which is much longer than this boundary layer thickness. And so if you imagine that you're like this little microorganism on the surface of the plate, and the thing is varying, you know, over 1,000,000 times your body length, basically from the point of view, your point of view, U plate is basically constant, and there's an oscillatory boundary layer on top of it, which is given by that formula, and then there's weak dependence on x. So this formula basically holds. Now one can be more precise about this, and you can spend an hour calculating the corrections to this, but I'm going to ignore that because I instead want to make another point. This formula basically still holds, and therefore using it, I can now calculate dyv, so I can write this is minus dxu, which is equal to, let's see, this is minus du plate dx times e to the I omega t times e to the minus 1 plus I y over delta. I have the y dependent, so now I can just integrate this. Now I'm not going to integrate it for you because I've already embarrassed myself calculating the square root of I. And integration seems like it's much too advanced. But what's going to happen is you're going to get a formula. So you guys can all go home. You should all go home. Someone said, are you giving us homework? And I said, no, but here, just consider, if you like homework, go do this. This is an interesting calculation. So you just have to calculate the integral dy, right? dy prime from 0 to y of e to the minus 1 plus I y over delta. And then it's times these factors, minus du plate dx e to the I omega t. Okay, so now there's a v. There's a vertical velocity field. Okay, so why do I care about this? So let's now consider the nonlinear inertial terms, which we, neglected. Actually, before we didn't even neglect. Before they absolutely vanished. So let's consider the nonlinear inertial terms. So let me just consider them. So if I write u dot grad u, well, for the x component, what is that? That's u dxu plus v dy u. And now you see that both of these terms are non-zero. And we have explicit formulas for them because that's v, and you have u, so you can plug it in, and they're both non-zero. Everybody agree? Does anybody not agree that those are non-zero? There's a u, there's a v, they're not non-zero. Now, on the other hand, they're small, right? I mean, at least if this thing is oscillating so much that it's once a year that it's oscillating back and forth, they're very small. That is, from the point of view of the Reynolds number estimate that we did at the very beginning of this lecture, then you should get rid of them. They're tiny. Because they scale, the size of these terms scales like the square of the velocity. And if the velocity is small, if the Reynolds number is small, then you should be able to neglect them. But yet, I claim that if you neglect them, you miss something fundamental about this flow. Anybody know what it is? This is sort of a test of how much.
Non-linearity?
What?
Non-linearity?
Well, there is nonlinearity, but remember, we basically said before that we were allowed to neglect the nonlinearity if the Reynolds number is small, and I'm telling you now that the Reynolds number is small, right? Because, I mean, look, I chose it to be small. I basically am going to make U plate to be small, and now I have a characteristic length scale of variation. It's the characteristic length that U is varying, right? And I'm going to divide by U. Make that 10 to the minus 100. I don't care. Just make it small. So the nonlinearity is supposed to be small, but yet I claim that if you neglect it, you're missing something fundamental about this flow.
Talking about acoustic streaming?
Yeah, so you know too much.
Yeah,
Okay,
it's
so-
pretty streaming, right?
Acoustic streaming. So anybody know who knows what acoustic streaming is? Okay, so acoustic streaming is the following fact, which was discovered by Warren Rayleigh, which I think is really quite remarkable. So although these terms are indeed small, let's now compute their time average. Let's time average the size of these things over a cycle. And I'm not going to do this calculation. This is an exercise for you to do. So time average means, what I would like you to do is take these things, and I would like you to integrate the integral of this from 0 to 2 pi over omega. So just do this integral over 1 second. You see, the thing is that U is sinusoidal, and V is sinusoidal, but it turns out that the phases of U and V, when you go through and do this carefully, are such that these integrals do not cancel. So you started out with this oscillating thing, but these integrals don't cancel. They're small, but they don't cancel. So what does that mean? If we go back to the Navier-Stokes equations, if the time average, if I take the time average of an oscillating thing, the time average of an oscillating thing is 0. If I take the time average of that U thingy over there that we computed, that's 0. The time average of that is 0. The time average of that is 0. But if the time average of U dot grad U is not 0, then the only way that these equations can be satisfied is if the velocity field of the flow actually gains a component that is not oscillating. That's the only way the equation can be satisfied. Because look, right, if this has a 0 time average, that's our own solution. That has a 0 time average, then the pressure has a 0 time average because it's basically just slaved by e to the I omega t. But that has a non-zero time average. The only way that you can get a solution is if there's also a component that's not oscillating. So this is amazing, right? So all of a sudden we took something that was oscillating and we said the nonlinearity was small, but yet the nonlinearity generated a steady flow. And that's called diffusion. And that's an example. This is just a simple example of where approximations can fail. And it's always the case that when the approximation fails, one of those things that are fundamental, these things, and that's but one example. So, okay, questions? This took much longer than I thought. Is everybody bored? Are you bored?
I'm not bored. I'm trying not to get bored. It's very, very interesting. There's just a lot of things I'm not getting. Are these notes going to be available for us to carefully look? Are you going to be available for questions?
Yeah,
No, I don't want to take up all.
No, I'm happy to. Sorry, I told you at the beginning, this is the problem with this lecture. It's like I'm doomed to fail. You're either bored or it's so I'm happy to spend time talking about this. Very interesting.
What's the name of the entry that the gentleman over there called that you said he was
too
much? Could you write that down?
Right. This is called acoustic streaming. Sorry. Yeah. So this is an effect that was discovered by Warren Rayleigh in 18-something or other. And basically, I believe Warren Rayleigh discovered it by taking a sphere, a small sphere, and he oscillated it with very, very small amplitude. And he asked what happens. Now, if it's a sphere, then locally on the sphere, as you know, as Copernicus, who is it that discovered that the Earth was a sphere? Not Copernicus. Anyway, somebody discovered that the Earth was a sphere. So as you know, that a sphere locally looks flat, which is the reason that people were confused for a while. So locally it looks flat. It's like a flat plate oscillating up and down. And so it's like this flat plate problem. But of course, the component of the velocity is actually oscillating. Is changing as you go around. So it has precisely the ingredients that I just described. That is, if the square root of nu over omega is much smaller than the size of the sphere, it has precisely these ingredients. And what Warren Rayleigh showed, when you oscillated, that actually if you put stuff far from the sphere, the stuff would get sucked in towards the sphere at a steady rate, which is very, very striking, right? And it is absolutely very flush. And it's useful, sure. But it's also interesting. I think it's philosophical interest. Is that? Yeah.
So in the first part where we were assuming still that there's no dependence on x, was because you started saying that we can make our own assumption, but still we learn. So the thing we learned was that we have this boundary layer. Is that
right? Right, exactly. So okay, so when we said U didn't depend on x, what we learn, so what you learn when you make these crazy assumptions, like let's consider an infinite plate, is you learn what happens in a certain limited case.
Yeah.
You don't know that that's what you're doing when you do it. This is why the subject is so hard to understand,
Yeah.
why lectures like mine are so hard to understand. You start with, it's an infinite plate, you say, well, there's no, but okay, but what we really meant by that, we then discovered from the calculation, is that we want the new plate to vary on a scale much larger than delta. We didn't know about delta when we
Yeah, so
started.
we learned what delta is.
We
which
learned
is
what delta was,
the
that's
decay
right.
of the y
That's
component,
right.
and then we can use that.
And then we can use that to describe the x direction. And if anyone likes math, you can basically, I mean, probably some of you have suffered through this. I mean, we could cover the entire blackboard calculating corrections to these things, and it's as boring as all hell. And I basically, I won't even do it, and I'm supposed to be a mathematician, so.
So a couple of questions. So the one observation, I mean, this is a beautiful example, but it's just anytime you have nonlinearity, you know, cosine squared, cosine omega squared, omega t squared as a constant.
Yeah, this can happen, yeah.
Whenever you have nonlinearities, they generate higher
So-
harmonics in a row.
Right, so one should generic, so it's, I completely agree with you. Generically, one might expect that nonlinearities, when things are oscillating, should lead to steady components. But the fact is that within the history of fluid mechanics, right, that is, you know, I mean, you can imagine getting yourself into the case where this is a surprise. I mean, I agree that these things happen. We all know of lots of cases where these things happen, but, you know, this notion of estimating and deleting is dangerous. That's what I'm
Well, and
trying to
also
say.
in this case, I guess it's this danger of deleting something compared to zero. I mean, in effect,
Right.
this is the only term
Yeah.
that's not.
That's right.
But the question I had is your x variation that you're considering of u is just on the scale of the plate? Is
Yeah,
that-
that's
that's-
right. I'm imagining it's like a sphere, it's like this chalk oscillating, right?
Right.
If the chalk were oscillating fast enough that the square root of mu over omega were much smaller than a piece of chalk, and there would be horizontally varying flows on those.
Right, so that's what that gradient is. It's one
That's what
over
that
the
gradient
size of the plate.
That's right. Other comments? Okay, I'm going much slower than I thought, but that's okay. Maybe these lecture notes will also work tomorrow. Okay, so, good. Yeah, so actually, for whatever it's worth, where am I going? So, just so that you all know, so the next, so there are 3 topics that are left in these lecture notes. So, you pass them around now. So, the first topic is dimensional analysis. I'm now going to do dimensional analysis, in which I think I'll spend most of the time talking about my theory of fireworks, but I think it will. Because we saw fireworks last night. And then I was going to describe to you the meeting organization in terms of deleted terms. Because that's why I didn't say meeting, because I thought, well, you know. But anyway, I think I'm going to ignore that. So this meeting is organized. I mean, you know, these guys, low Reynolds number, high Reynolds number, everybody has, you got that. But then I was going to do 2 main calculations today. And the one calculation that I really want to do that is not going to get done today, but that I will do next time, and then we'll see where we're going to go, is I want to actually describe Pronto's discovery as boundary layer T, which is, I think it's an example of this, but I want to try to describe to you what the historical context must have been and try to explain to you why you all should know about Pronto and why his discovery was so important. It's something which is much in the spirit, but I think it's worthwhile going through it because it just sets so much of the intellectual foundation of the subject. So that's where this is going. And then I was going to do another calculation at the end of these notes on low Reynolds number boundary layer theory, basically, which is called limitation theory, and then we were going to go on from there. So that's what's in the notes, some fraction of the time. So okay, so I now want to do dimensional analysis. So, seems sort of boring. Okay, I'm going to just do a couple of interesting examples. So, dimensional analysis, the way that it's usually told, so I'll criticize the way it's usually told. So, you know there are these dimensionless numbers. I told you there are all these dimensionless numbers. Everyone has their numbers. And then, of course, the equation relates all of the dimensionless numbers to each other. So, there's this notion, blah, blah, blah. Because, you know, there's, if there are many dimensionless numbers, then they all have to be related in particular situations. So, there's this whole notion that you should figure out the relationship. But then usually what happens is, so there's this thing called the Buckingham Pi theorem, which is described in the notes, which is the formal theorem of this, that anyone's interested, you should go and look at. But then what you're then supposed to do, if you're giving a lecture on dimensional analysis, is then you're supposed to do lots of cool examples that make everyone very happy, which actually require lots of physical insight and are not algorithmic at all. And so now I'm going to just do this. Okay. So, because that's more fun. Instead of going through the formal stuff, because you can do that. Actually, the reason that this is important, this isn't really quite dimensional analysis. So the reason that what I'm doing, I think, about you is important for as an introduction to this school, is that you will find that many of the lectures that you will hear, so the lecturers all have different styles. Some lecturers like to compute the 4th term in the perturbation expansion to show you how small something is. some lectures like just estimate things and tell you the sizes of things and then go on. And dimensional analysis, as I'm about to do it, is really about the latter. And you will see many people will get up and sort of make essentially dimensional arguments. So it seems reasonable, therefore, to just consider them in a generality. So I have a list of various things that I'm going to do. I don't know. I'm not going to do them all. I want to do fireworks, though. That's what I really want to do. Does anybody know how to prove the Pythagorean theorem by dimensional analysis? Does anybody not know this? It has to be one person who knows, right? Who doesn't know how to prove the Pythagorean theorem by dimensional analysis? Leah, you don't know this? Oh. Okay, so then I'll tell you. Okay, so here it is. Sorry, this isn't my notes. If you know it, okay, so here it goes. Okay, so this is a triangle. It's a right triangle. It has a hypotenuse that I will call L. So like Z. It has some interior angle that I will call phi. Okay, now the area of this triangle has the dimensions of length squared. And there's only one length in this problem. This completely characterizes the triangle, and so this is just given by L squared times some function of phi, which I will not even calculate. So there's some function of phi. So this is the only dimensionally consistent formula with the notion that this is an area. So and this formula has to apply to all right triangles, because I just took an arbitrary right triangle. So okay, so now what I'm going to do is take this and bisect this angle. I'm going to make two other right triangles. And where did it go? And now actually I have two right triangles, and the hypotenuse, this is not blue, it looks blue, the hypotenuse of these two right triangles are respectively A and B. And this one has an interior angle phi, and this one also has an interior angle, which is also phi, because if you sort of go do trigonometry from high school, you'll determine that that is phi. And so these two little right triangles also have areas, and the area of this guy is A squared f of phi, and the area of this guy is B squared f of phi. And so, since the area of the two triangles is the same as the area of your intertriangle, that is now proved using Pythagorean theorem. Okay, very good. Just fine. Okay, so now, let's see. I know it's boring. Okay, so now, does anybody know what the density of water is? Kilogram per meter cubed? Gram per centimeter cubed? Does anybody know what the density of ethanol is? Okay, does anybody know what the density of motor oil is? Motor oil? Motor oil? How is it like 100? What is it? Is it two guess?
It's got to be around 700 or 800 kilograms per meter.
Motor oil?
20.
20? You think it's 20? Yeah. So has anyone ever noticed that all matter has about the same density? Isn't that interesting?
You're talking about the air on this?
The air doesn't. All solid matter has the all fluid matter has the same density. It's basically the same. It doesn't change much. Isn't that
What about Mercury?
Who?
Mercury.
What's the density of mercury? You're on the web. You can tell. It's not bad.
It's 9 times the density of water.
It's 9 times? Okay, good.
So
So if everything has about the same, except for mercury, we can talk about mercury, then it makes sense that you should be able to calculate it. And I actually, you should be able to calculate the density of water. Has anybody ever calculate the density of water? First principles. Okay, here, I'm going to tell you my calculation. Here it is. And it's going to work for all fluids. It's going to be wrong for mercury, but we'll have to study why. So basically, what is a fluid? So there's mass. The mass is basically a proton. So it's basically the mass of a proton divided by a Bohr radius cubed. I'm not going to actually. The Bohr radius, actually, I was going to calculate the Bohr radius for you, but I'm not going to do that. So the Bohr radius, you can also calculate from dimensional analysis. The Bohr radius is whatever. It's this thing you want to formula as h bar squared over the mass of the electron times e squared. And this is about a nanometer. So the Bohr radius is the reason that the nanometer is the relevant, is an important length scale of light, which you all know. And this, if you calculate this, and I would encourage you to all go through this, I did this, I got that this was 1.4 grams per cubic centimeter. That's pretty good. So now you can, probably you can now make a theory of mercury if you want. You guys can go home and make a theory of mercury. So what's so great about this argument is that, yeah, it gave us 1. You can see you can't have something that's that much smaller than 1. It's just impossible. If someone came and told you I have a liquid, right, that has a density of 10 to the minus 2 grams per cubic centimeter, it's one interesting liquid. Now you know, actually, what the definition of interesting is. And so now you can make theories. So that's pretty good. So, okay, that's the density. So what about the viscosity? Does anybody know the viscosity of water? Does anybody know? Let's do the kinematic viscosity. the problem with viscosity, right, there are these two viscosities. Right, there's eta, right, and then there's nu, and eta is equal to rho times nu, but I already did rho, so I'm going to just forget about rho. So let's just do nu, which is the diffusivity part. So this has the dimensions of the diffusion constant. Does anybody know what the diffusion constant, what the viscosity of water is?
It's 1,000 SI units.
Viscosity of water? This is an important number. This is a fluid mechanical number. Hey, do you know viscosity of water? Thank you, very good. Okay, so big with viscosity of water. So the viscosity of water is 10 to the minus 2 centimeters squared per second. Anybody know the viscosity of ethanol? Want to guess? Ethanol. Methanol? Octanol?
I know less than this.
Same.
So actually, most things have the same viscosity. Does anybody know something which has viscosity which is much larger than the viscosity of water? Glycerol. That's interesting. Glycerol is good. Okay, does anybody know anything else?
Silicon oil.
Silicon oil. Okay, good. Okay, good. So let's calculate the viscosity of water. Does anybody know anything which has a viscosity much smaller than the viscosity of water? Liquid helium. That's an interesting case though, right? See what you had to do? Look what he had to do to get something that was smaller. He went to like the most exotic, you probably had summer schools on that. See? They've had whole summer schools on it. So, okay. So how do you calculate the viscosity of water? So, well, let's see. So, nu, the dimensions of nu, well, it's length squared over time, because it's a diffusion constant. And so this is the same as, of course, a velocity times a length. Times a length. So can anyone tell me what the relevant velocity is in water for characterizing its viscosity? No, so people who have seen this before aren't allowed to answer. But they said the sound speed. So I'll just tell you. I mean, it's because, look, if you look at molecules in water, if you just imagine the picture, it's jiggling around with sound speed. That's what it's doing. Can anyone tell me the sound speed of water?
Let's say the sound.
1480. There's 1480 meters per second. So it's 1480 meters per second. Okay? We could do calculating that too, but we're not going to do that. That's not for today. So does anybody know what length scale is relevant for water? We need a length scale. It's water. Just imagine it's jiggling around. What do you think?
It's the length between the
Nanometer. Yeah, it's like the size of the molecule or something. It's something like if you know too much, like hydrogen, forget that. It's just like a nanometer. Nanometer. Okay, good. So now we have to multiply times 10 to the minus 9 meters. Okay. So I'm going to do this in centimeters. So this is 10 to the 3. This is 1.5 times 10 to the 3 meters. So this is 1.5 times 10 to the 5 centimeters per second times 10 to the minus 7 centimeters. And that is equal to 1.5 times 10 to the minus 2 centimeters squared per second, which is within a factor of order unity of viscosity of water. So isn't that amazing? So what this means is that you can actually calculate, you know these parameters that you're given when you're young, that are in these books, you can calculate them all. And actually, when something doesn't agree, then all of a sudden it becomes interesting. So for example, Kate said glycerol. So actually, let's dispense of silicon oil first. Does anybody know why silicon oil has a higher viscosity than that of water? Yeah, it's a chain polymer. There's all this crap in it. So if you have a thing with a lot of crap in it, then does that change the sound speed? What do you think? What it mainly changes is the length scale, right? The sound speed actually doesn't change that much. This is actually an interesting calculation. If the school went on for a year, then we could actually now calculate the sound velocity of a mixture of crap with crap in it. And we would find that if the volume fraction of crap was not large, then it wouldn't change very much. That's what we would find. But if you have these things around with length scales in them that are reasonably big, now the length scale, so like what's the length scale of a polymer chain in silicon oil? I don't know. Instead of it could be 100 nanometers, now you've got a factor of 100. So now I have a hypothesis. This is why this is so great. So my hypothesis is that your silicon oil, which has 100 times the viscosity of water, has chains that are about 100 times the size of a water molecule. It may be wrong, but it's a hypothesis. How long am I supposed to talk about? 10:30 or something? According to this, I'm supposed to keep talking until 10:30. Okay, good. So good. Because you have to do fireworks. Actually, okay, but what about glycerol? Does anybody know? Let's do glycerol before we do this. So glycerol is interesting. Is glycerol, what is glycerol? Is it a polymer, a simple liquid? What is it? It's a simple liquid, right? So why is it that the viscosity of glycerol? Does anybody know what the viscosity of glycerol is at room temperature?
80.
How much more is it than water? 80? At room temperature. So at room temperature, the viscosity of glycerol is 1,000 times the viscosity of water. It's a factor of 1,000. Simple liquid. Does anybody know what the size of molecules are in glycerol? About again, about the same. Think the sound velocity in glycerol is very different than that in water?
No.
I think. I don't know. We didn't calculate the theory of sound, so but you know, I mean, come on, it's dp d rho, like kT over the mass. It's that'll work pretty well. So okay, so why is glycerol? Does anybody know why glycerol has a viscosity that's 1,000 times that of water?
Is it because it's non-Newtonian?
No, glycerol's pretty Newtonian. So remember, Newtonian is Newtonian versus non-Newtonian. Non-Newtonian means that that there's a nonlinear dependence of strain of shear rate on strain, stress on strain. Sorry, stress on strain. So, but the prefactor of the linear relationship between stress and strain is the viscosity. And so the viscosity can be large and have it be perfectly Newtonian. Glycerol's Newtonian. That's not the problem.
Maybe hydrogen bonds can make structures larger than the scientific.
Okay, good. So that's good. So now we're getting there. So okay, so there's something going on in glycerol which is peculiar, which is basically making structures larger than the size of the molecule. So it turns out that glycerol, the blast transition in glycerol is, do you know what the blast transition in glycerol is? It's just below, it's like minus 50 C or something. It's not that far away. And basically, as you all know or may know, that when you approach a blast transition, the characteristic length scale of the structures actually diverges. And so essentially what's happening is that we're feeling at room temperature the remnant of the blast transition, the phase transition of the material that's not too far away. So, okay.
It's 1,000 times the length.
And according to this hypothesis, 1,000 times the length of and you can go test this, maybe it's wrong, but you know, it's okay to say things that are wrong as long as they're interesting. No, I'll rephrase that. As long as you learn something from it. That's what I meant to say. People say things that are wrong that are interesting. Okay, so let's see. I have, I was going to calculate the radius of the Earth. Sure? We're okay? Or we could, okay, we're not going to get to Prandtl today, but okay. Let's calculate the radius of the Earth. Okay, so actually this idea, the idea that I'm about to show you, calculating the radius of the Earth, I stole. There's this wonderful article by Bill Press that is called On Man's Size. Here, it's in here. So yeah, it's called On Man's Size. Actually, the reference is down here. The reference is here. Actually, no, it's called man's size in terms of fundamental constants. So he tries to calculate man's size in terms of fundamental constants. He gets like a centimeter. But anyway, in the middle of the article, he has this very interesting argument that basically calculates the radius of the Earth. So, so let me show it to you. So, okay. So, let's see. How are we going to do this? The radius of the Earth. The Earth is made out of ordinary matter. What's the density of ordinary matter? It's 1 gram per cubic centimeter. So therefore, if I have the Earth, which has a mass, m Earth, and has a radius, r Earth, cubed, well, that's the same as the density of ordinary matter. And I already told you what the density of ordinary matter was. That's the mass of a proton over a Bohr radius cubed, which is 1 gram per cubic centimeter. So the Earth is ordinary matter. So you see, this formula gives you one relationship between the mass and the radius of the Earth. And in order to close it, you need one more relationship. And here's the relationship that I will give you. I don't know if you like this. So, and this is more or less what Bill Press says. So so basically, the game is that the atmosphere of the Earth. So if you have a constituent of the Earth's atmosphere, if it is moving faster than the gravitational escape velocity, then it will go away and it won't be there. So remember, the gravitational escape velocity of something is just given by, so one needs the kinetic energy of that thing to basically be in order the gravitational potential energy So that's, so let's see. So I need V squared to be a border G and Earth over Earth. So this is what I need. So I need the velocity of something that escapes to be larger than this. Now, the constituents of the atmosphere are, of course, running around with their sound velocities. And and what Bill basically pointed out is that the Earth's atmosphere has no hydrogen in it. There's really no hydrogen in it. So that means that the velocity of the hydrogen, I mean, there is oxygen, which is heavier than hydrogen, but it's not a huge factor. So, I mean, there are things that are slightly heavier. So that means that the escape velocity, that's the critical velocity at which things escape, has to be between the velocity of, say, hydrogen and the velocity of, say, oxygen. But you might as well just set it equal to the sound velocity of hydrogen, because, you know, these are factors of order unity. And so the sound velocity of hydrogen, which is just a gas, is given by kBT. Kb is Boltzmann's constant, T is the temperature, divided by the mass of a proton, because hydrogen, of course, has a mass. It's only the mass of a proton. And now you see I have two equations and two unknowns. I have two equations and two unknowns. And so now I can solve for our Earth. And so I solve for our Earth. And this is the formula. So you get our Earth is equal to the Bohr radius times the following dimensionless number, kBt, divided by the gravitational interaction of a proton with itself that is separated by the Bohr radius to the 1/2 power. So this is the thing. And T, of course, the temperature on the Earth is 300 Kelvin. And the numerator is an energy and the denominator is an energy. And so if you put in numbers for this, then what you get is, of course, this number is enormous. This is an enormous number. But what you get is that you get the answer that this is 1.8 times 10 to the 8 centimeters. And if you compare it with the actual radius of the Earth is 6.4 times 10 to the 8 centimeters. So it's within a factor of a couple. Yes.
So question, what was measured, well, what number appeared first? The radius of Earth or the Bohr radius?
The radius of the Earth.
So why not estimating then Bohr radius from the radius?
You can do that. Very good. Okay, so you can do that. That's very good. That's actually, I hadn't thought about that. That's actually much better. So I'll tell you, so the other criticism of this, so I was really very happy about this, because that's so cool. You can actually calculate the radius of the Earth. Like, who would have thought, like, the radius of the Earth? Like, these are numbers that you're supposed to look up in books. And I ran into Paul Chaikin, who probably has been a lecturer in this school. Has Paul been here?
He has been.
He's been a lecturer in the school. So I told Paul this argument. I was so happy. I said, Paul, look, this is so great. You can calculate the radius of the Earth. And Paul looked at me and said, as he always says when I say anything, he said, that's stupid. He said it in the nicest possible way. And he said, listen, he said, you know, imagine that you're doing a measurement. How hard is it to measure that there's no hydrogen in the atmosphere of the Earth? That's a really hard measurement. What's much easier is just to drop the piece of chalk and to measure its acceleration. So he said, you know, this is stupid. You shouldn't be using this formula because that's a hard measurement to make. So the easier formula to use, of course, is that G is equal to G Earth over R Earth squared. Because you can just measure a little G. And then you get the radius of the Earth. And if you do that, as it says in the notes, you also get this very nice formula, which gives you the right answer. So, okay, good. Questions? I don't know, I mean, to me, I know these are a bit silly, but to me, anyway, these were very eye-opening calculations in the sense that I didn't know you were allowed to ask what the viscosity of water was. I mean, you know, I always thought that was something that chemists should do. It was very, very complicated. Whereas, in fact, you know, the CRC, like you open up the CRC, and it's like this terrible book. There are all these numbers in it. And you're like, what are all these numbers? But what they should really do is publish, in fact, maybe you guys, somebody with the dimensionless CRC. So you should divide every number by what it should be. And then you can see which substances are interesting.
I thought that one of the impressive things that I'm looking is that we didn't have to measure the mass of the Earth anymore.
That's right, we have the mass too.
Whereas in the first one, you do need the mass of the Earth.
No, you get the mass for free in both of them. So these are two equations and two unknowns in both cases, and so you get both formulas for the radius and the mass. Remember, if I know the radius, since all matter has the same density, I also know the mass. Which is pretty good. Okay. So now let's get to fireworks. Okay, so first I'm going to show you a classical calculation about explosions that probably many of you have seen, and then I will tell you about my meager efforts to use it for understanding the fireworks that most of us saw last night. So the classical calculation is one that sort of, you're always supposed to say it when you talk about dimensional analysis, but it also really, I mean, I think at the time it was invented, it was one of the first of its kind. But I mean, you know, human beings discovered that you can argue in certain ways, and I would always posit that this was early on in the days that people learned you can do this. And this basically is goes by the name of Taylor's blast. And I'll tell you the apocryphal story as it goes, and then I'll derive a formula, and then I will use it. I'll try to use it for fireworks, and we'll see. And it's going to fail, but then you guys can figure it out. So Taylor. So this basically goes back to World War II, when, as the apocryphal story goes, he was shown. There was a. This story is actually not true, but it's such a good story. I mean, you know, the thing about stories is that once they become very good, even if they're not true, then you keep repeating them as they were when they were good. I don't know. I mean, there's this great book. Did anyone read The Life of Pi? There's this great book, The Life of Pi. It was basically about this. It was about a kid that was on a boat that was going across the ocean, and there was a tiger. There was no food on the boat. The whole book, the kid was, it was a little boat. It was like this big, and the kid was trying to get away from the tiger. And the kid was worried he was going to get eaten by the tiger. Then basically you're reading this book, like, what's going to happen to this kid? He's going to get eaten by the tiger. And then at the end of the book they said, well, that's one way of looking at the story. There's another way of looking at it, which actually probably is true, but it's not nearly as interesting. So let's go with the first version of the story. So that's sort of like this story. It's not true, but it's kind of. So the story is that Taylor. So there was the atomic test explosions in the 1940s, and there was a picture on the cover of Life magazine with the blast wave from the first atomic test explosion, and Taylor called up his friends, Los Alamos, and said, "Could you guys please tell me the energy of the blast?" And they said, "No, we can't tell you the energy of the blast. That number is classified." And so he then proceeded to compute, as the apocryphal story goes, the energy of the blast from the picture. And this is how he did it. So he said, "Look, you know, there's something that's going to explode, and it has some energy. You know, there's some energy that's stored in the thing that's about to explode, and when it explodes, what it does in making the blast wave is it pushes the air out of the way." Now, air, that is ambient air, is characterized by really two numbers. There's the density of the air, and there's also atmospheric pressure, right, which is pushing out. And Taylor basically surmised that, you know, so air has two numbers, the density and the atmospheric pressure. And he said, you know, this was really a very, very big explosion, and so I'm going to just pretend that atmospheric pressure is irrelevant, because I'm just going to say that the pressures that are being created by this thing are so large that atmospheric pressures are irrelevant. And then he said, can I now write down a formula for the radius of the blast wave, asserting that these are the only two parameters that are relevant in this problem. And what he noticed was that if you consider the ratio of the energy divided by the density of air, that this number has dimensions. And so the dimensions of this, so energy, of course, is mass times velocity squared. So that's mass times length squared over time squared. And density is mass over length cubed. And so then the point is that the masses cancel, and this thing has the dimensions of length to the fifth over t times squared. So the dimensions of this quantity, E naught over rho, are length to the fifth over time squared. And then the idea is that let's suppose that there's some law that basically states that the radius of the blast wave is increasing as a function of time, where we're going to take t equals 0 as being the initial time. The point is that I have to write down some dimensionally consistent formula for this radius. So what I know is that the radius, according to this theory, is a function of the time, and it's also a function of this parameter E naught over rho. And I have to invent some formula that basically captures that. And Taylor's point was that there's only one formula that you can write down that does that. Because if you want this to have the dimensions of length, what you have to do is take E naught over rho. You have to multiply by t squared. This quantity now has the dimensions of length to the fifth. And then you have to take the 1/5 root of this formula. And that gives you the radius. That gives you the radius of the blast wave. And the story is that he simply plugged in the numbers for the time and the radius and calculated the energy. One can do a much more careful version of this calculation, which he then also did. Von Neumann and Sedov independently did the same calculation at the same time, in which what he did was he actually took the equations that we wrote down at the very beginning, the really messy, complicated ones, and he actually constructed a solution which actually, for a blast wave, which grew according to this law. And when he did it very carefully, he was able to calculate the prefactor of this law. There's actually some constant, there's some dimensionless number which you don't know, and it turned out that this dimensionless number was about 1.1 or something crazy like this.
1.01.
1.01. See, that one he hasn't memorized. It was very small. It was very close to 1. And I don't know, this is sort of apocryphal, but people say that you know those dimensional numbers, that always happens, so then you can always do this. I don't know if that's actually true. I mean, sometimes as, one gets messed up by pies. Okay. Anyway, so that's the blast wave. So last night after the fireworks, we were all talking about, well, we should really, talk about the physics of fireworks. So and actually, we were having this conversation when we were watching the fireworks, for those of you who weren't there, that there were claims that, you could make fireworks have shapes like hearts. We didn't see that last night. You guys don't have heart-shaped fireworks here. Did you?
If you look towards the north, the cities, these rich suburbs of Denver, theirs were very well funded, much better show, and there was heart-shaped like that. You need to look towards the rich suburbs. That's what they do with their tax money. There's shaped hearts. And
okay, so we were trying to figure out, how can that happen? A heart. Anyway, so I'm going to just give you an opinion. I basically thought, so I was trying to figure out, what calculation can we do? So last night, I basically decided, well, maybe the one calculation that we can do is we can calculate how far, when you watch fireworks, at least in Boulder, they were basically all spheres. There are a couple of rings, but you guys they were basically spheres. So in Boulder, you only have to explain spherical things. Now, we can talk about the non-spherical ones when we're done with the spherical ones, but let's talk about the non-spherical ones. So I thought, well, maybe what we can do is we can explain the radius of those things that we saw. The lights coming out? You guys saw this. So there's this thing that went boom, and there are all these lights. And so I was like, radius. So I was like, maybe we can explain that radius. That was what I wanted to explain. So I want to explain that radius. So there are two options for this. So one thing you could do, and this was the part, is that you could say that, well, look, so the light, these things are exploding outwards. They're of course exploding outwards according to this law, I should say. Now Detlef, actually, he may or may not show this in his talk, there was once an explosion in a fireworks factory in Enschede, which was right next to where Detlef works, and maybe he'll show it to them sometime, maybe you don't have to. But anyway, there's a movie, someone took a movie, basically of the blast wave, and they then fitted this beautiful teeth into a fist, and they used it to basically figure out the total energy that was a fireworks. It was in the fireworks factory. So these things actually, this is a really good law. It's not. At least as long as the assumptions hold. So anyway, one thought for what's setting this radius is that there's some amount of time that the lights are on, because there's some chemical reaction, right? It's basically going on. It's causing them to turn on. So imagine that the lights were on for time tau. So tau is equal to time that lights are on. And that's some chemical time. I don't know what it is. It depends on the chemical reactions that are in the fireworks. Then one hypothesis that you might have for what was setting the radius is that you take this formula, you take Taylor's formula, so this is R Taylor, and you simply evaluate it at that time. So that's one formula. Now, if that were the answer, it would be very depressing, because then you have to go, and I just was too tired last night to do this, to go and look up the characteristic time for the lights to be on in fireworks reactions. But so, yes?
Why is it clear that the Taylor formula should work here? Because for the explosion, it was homogeneously pushing air out of the way, whereas for a firework, it seems that it's discrete objects, the sparklers or whatever, that basically light up and are shot out as projectiles.
So there are things, so my view of this is the following. This may be wrong, actually. In fact, everything about this may be wrong. Because it's shot up, as a projectile. It's got some mass. It's given some momentum. The heavier it is, and this is important, actually, if you're thinking about the design of fireworks, the heavier it is, and then for a given momentum, right, it won't go as high, right, because you're giving it some kick. I don't know how we're giving it some kick. There's probably some other explosive on the ground that's giving it the kick, actually. So it goes up, and then what I'm imagining is at that point, it explodes. Because that's what happens. You see the from the points in space. That's what you see. So I'm basically now asking, once the thing goes up, it hits the point where it explodes. There's some timer or something in it, and it goes, and I want to calculate the radius of that. And there's all this crap that comes out. I don't know what it is, and we're going to talk about this, but for the moment, but you would imagine that that blast wave. So I mean, there is an issue of whether or not, and this is actually very important, and this is sort of whether or not the light wave actually corresponds to the blast wave. So the blast wave, a la Taylor, has the following feature. If you were to plot the density of air as a function of radial distance outwards from this thing, it's going to look something like this. That is, it's going to basically asymptote at the density of air, and in the middle there's going to be some depletion, basically, that's going to exist. And this is the radius, this is RT, and in the full solution to the Euler equation, this is the radius that's propagating. And there is a real question of whether that's going on. But anyway, this is just, let me tell you my calculation and then you can yell at me.
I guess what I'm saying is, if your calculation is wrong, my guess is because in the Taylor calculation, that bunt you talked about, where the density falls off, is the same as where the light falls off. Or the same thing that's true for the fireworks.
Okay, so let me show you my calculation and then we can talk about how it's going. So now this is one calculation, but the problem with this calculation, of course, which actually could quite well be true, is that now you have to look up the time for fireworks. So what I decided to do instead was to ask, well, what was the biggest the thing could possibly be, this radius? And the biggest that it could possibly be is basically once the energy density in this front, in the fireworks, becomes an order atmospheric pressure, it will stop pushing on that. It will stop accelerating. This thing is accelerating. It will stop accelerating. Namely, I actually, right, remember we neglected in Taylor's calculation the atmospheric pressure, and I can now ask, actually, at what radius does the atmospheric pressure come in? So now I'm asking a question, at what radius does atmospheric pressure matter? So let me call it radius atmospheric pressure. And that radius actually only depends on two things. It's a function of the energy of the blast and atmospheric pressure. That's the radius at which the atmospheric pressure is actually pushing so hard that this thing can no longer continue to explosively expand. And going through the same thing, I mean, pressure, of course, is an energy density. Pressure is an energy density, right? Pressure is an energy density. So that means that this formula, I think I might have done this wrong. Maybe that's my problem. So this is E naught over P atmosphere to the 1/3. That's what that is. It's E naught over P atmosphere to the 1/3. Actually, I did it wrong. So in the notes it says the square root. Let's see, this is why I was nervous about the square root. But anyway, now you have it.
It's two-dimensional.
No, but fireworks are three-dimensional. So, but that's the ring. So we did the ring. Okay, good. Okay, so then I actually was interested is, well, what is this number? I mean, what's the number? Right? And I was sort of hoping it would come out to be, I don't know, how big, does anybody know how big those things were? Just roughly, what do you think they were?
20 meters.
20 meters. See, that's sort of, 20 to 100 seems reasonable. It's sort of hard to tell because we were far. Some of you were closer, I don't know. Did anyone watch it from the football stadium? So how big did they look like from you? Because you had it close. Was it as big as the football stadium?
Yeah.
Yeah, so it's like 100 meters. Okay. So I needed to know the energy. So to know the energy, you have to know what fireworks are made of. And I actually don't know what fireworks are made of, but it's easy enough to look up the energy density of TNT, which seems pretty nasty. So the energy density of TNT, TNT, which must be what, I don't know if anyone knows what fireworks are made of, but I mean, it turns out this is 5 megajoules per kilogram. 5 megajoules per kilogram. So now if we want to know the energy, we have to multiply by the size of the fireworks. So the size of the fireworks is constrained because the bigger it is, the harder it is to get it up in the air, and there's some explosive on the ground. So you really want to do this, you have to work that out too. And I didn't have time to do this because it was really late last night and I was sort of tired. But so I don't know how heavy a firework is. Does anybody know? I said that it was 100 grams.
What category?
Oh, good. Okay, if you make it bigger, it'll be better for me. You think it's a kilo? Have you ever picked out a firework, like big ones? It really is. Okay, good. So that means that, good. Okay, so let's say it's a kilogram. So let's say the mass kilogram.
Yeah, but there is something still. What we're estimating is not the mass of the stuff that is actually launched.
That's right.
The 1 kilogram is the
Of the
mass
TNT.
that actually
It
launches
explodes.
and the stuff that
Exactly.
explodes.
This is the exploding mass. That's what we're doing.
So the exploding mass.
But but if she says it's 1 kilogram, then she'll probably give you 2 kilograms, and so we're doing work. But anyway, we'll see what happens, and you can see what happens with this number, and then you can decide. I don't. But this is why I think this is interesting. So now we have 5 megajoules, and it turns out that atmospheric pressure, P atmosphere, this is something that you should know. It's 10 to the 5 pascals, which is 10 to the 5. So that's the CGS units. That's the same as joules. So it's 10 to the 5 joules per cubic meter. So now I have 5 megajoules divided by, so now we have to do this calculation. Okay, here it goes. This is so exciting. Let's see. So you're going to give me a factor of 10, but I have a cube root, so you're going to be in trouble. So okay, so it's E naught, so it's 5 megajoules. So that's 5 times 10 to the 6. 10 to the 6 joules over 10 to the 5 joules per cubic meter. I'm supposed to take the 1/3 root. So that's the cube root of 50. What's the cube root of 50? It's like 4 meters. Ouch. So actually what's interesting though about this calculation is that even if that time tau were 1, so you can't use that formula beyond 4 meters. You're not allowed. This is what's interesting. You're not allowed to use that formula beyond 4 meters because once you get up to 4 meters, what this is telling you is that at that time, which we can calculate explicitly from this formula, the assumptions of that formula, that theory break down and it's gone. And so that means that there must be something else going on. So anyway, I had the following thought, and then I'm going to stop because I'm now slightly over. So this was my thought, but this is just something for you to think about. Is that so? When this happens, there are, as was stated before, projectiles in this fireworks. Like there are things that are going outward. So my thought was that maybe this radius is the radius at which the projectiles are no longer being accelerated from the explosion, and then of course they're going to follow gravitational trajectories. So they're going to be launched with their velocity, and that velocity is presumably very large. It depends on the mass of the projectile, what that is, and it will go out as far as it does, and then it will fall. And that's actually going to give you a much bigger radius. So the other thought that I had is with respect to these fancy communities with the hearts, and things like this, is that so I don't know if this is right, but it just occurred to me that the fact that this number is small might be a good thing for making different shapes. Because, as somebody said last night when we were talking about heart, you said it in the back, or we were talking about heart-shaped fireworks. And the way to make heart-shaped fireworks, of course, is to launch them in the shape of a heart.
Actually, they time the secondary explosion.
But that's the same as launching them in the shape of a heart, right? But that is, we can either launch them all at the same time from a heart, or we can time the secondary explosion so that the front is in the shape of a heart. And the point is that if this length scale were very, very large, you would not be able to do that. Because what that would mean is it would be washed out, basically, by a spherical explosion. So anyway,
But your calculation might work because if you look at fireworks, they typically have like a central corona, right, which you're pointing out, and then they have the projectiles. And the corona is like 1/10 to a quarter of the actual size of the big thing, which would agree more with your formula.
Very good. Okay. So, but this was the thing. So what's good about this, so just to summarize, so what's good about this way of reasoning, which you will see repeatedly throughout this school, is that, even if it's wrong, it sort of explains to you what's going on better. So there you go. So now, that's it. So now we'll... So I think we're on a break. We're on a break. I'm just...
for the lecture.